Having looked at an introduction to vertical circular motion, and then having had a look as well at the general method for finding the change in height during circular motion, so that's two previous videos to this one. Now it's time to start having a look at a few things in a little bit more detail, and this is the first of two broad categories. This first one is just a single case, just a category all of its own, but then the second category will have to be broken down into a few different cases as well. So these two categories are whether the object is in a fixed vertical circle, it can't leave the circular path, or whether it's in a situation in which it could at some stage, given certain circumstances, it could at some stage leave that circular path. And we'll have a look at a variety of different situations and conditions under which that might happen. But first, in this video, I want to look at the case where the particle is fixed in its vertical circular path. And so there's a couple of examples that I've listed up there of types of situations that fit this sort of scenario. It might be a particle at the end of a rod, so you've got, like, a length of stick, a ruler, or whatever it might be, a particle at one end fixed at the other end, so it's going to rotate about one end, and then a particle on the other end is just going to go round in a circle, and it can't leave that circular path as long as the other end is fixed at the centre of the circle. Then the particle is constrained to stay in that circular path whatever happens. It might not make a complete circle, and we'll talk about a little bit about that, but at least it can't leave, it can't be anywhere apart from somewhere on the circumference of that circular path. And we're going to have a look at this kind of situation just for the sake of keeping things relatively straightforward for now, assuming that the situation starts with the particle at the bottom of the circle and given some speed u at the bottom of the circle. And then we're going to be interested in finding out things, what happens as it goes around some general point around the circle. So if you can imagine this sort of situation, there are really two possibilities within it, depending on how much speed you give it to start with at the bottom of the circle. Either the particle will start down at the bottom here and go up a bit and then sink back down again, if you just gave it a little bit, and then it'll do oscillating motion. Assuming there's no loss of energy in the system, it'll just keep oscillating between the two extremes in a kind of symmetrical sort of pendulum style of thing, and it'll just keep doing that forever. If you give it a little bit more speed at the bottom, you might just be able to give it enough speed for it to keep on going until it goes right up to the top, and then keeps on going all the way around, and it performs complete circles. So those are the two categories. Obviously, the first category, where it's becoming a pendulum, it needn't necessarily go high. It could just be tiny little movements down here or something like that. It depends how much speed you give the particle at the bottom of the circle to begin with. So we want to have a little look at that, at how to analyse situations like that. Now, as I said in previous video, I've shown you how to look at change in height, and we know now that the most efficient way to handle analysing vertical circular motion is to take an energy approach to it. And so we're going to be looking at changes in gravitational potential energy, balancing out changes in kinetic energy. And for the GPE bit, we know from the other previous video that we've got a good neat technique for finding the change in height. And so we can just launch straight into this. If we take an energy approach to this, we can see that it starts with some kinetic energy, and the kinetic energy is going to decrease as it goes up the circle. So we're going to have a KE lost, and that's got to be balanced out by a GPE gained. So just a reminder, as I'm finishing writing there, we can do this because we've got this constraint on the whole situation where we've only got the two forces acting on the particle, just a weight force, which you can see that I've labelled on my diagram here, mg vertically downwards, and then one other radial force in any of these situations that we're looking at, and here the radial force is a tension along the rod. And this tension along the rod here does no work because it's always perpendicular to the direction of travel of the particle. And the work done by the weight force here is just exactly the same as calculating the change in gravitational potential energy. So we can just balance out the two types of energy here. So we've got KE lost equaling GPE gained. KE lost clearly is going to be half m u squared minus a half m v squared. And GPE gained, I'm just going to take this straight from the previous video, we had as being mgr, where r is the radius of the circle, and then we open up a bracket and have inside our bracket 1 minus cos theta, where theta is the angle that the rod has turned through from the bottom. So here's our equation, our energy equation in the most general sense for this sort of situation. We can see that there's a mass term which will cancel out throughout this, so that tidies things up. It might be a bit more convenient if we multiply everything by 2 as well to get rid of those halves. So we're going to end up with a situation where we've got u squared minus v squared being equal to 2gr times 1 minus cos theta. And probably what we're going to need in most situations in these sorts of problems is we're going to need an expression for v, or well, let's leave it as v squared rather than bothering with square roots. So I can rearrange this thing to get v squared as the subject of this equation, and we've got v squared equals u squared minus 2gr brackets 1 minus cos theta. And so this is a nice general equation. You should not quote that, please. If you have to use that in an exam question, for example, it's something that needs to be derived each time. Don't take that as a thing to memorize and just use. You need to get that each time you do it. Generally speaking, when you do exam questions on these, the information given tends to make this process a little bit easier rather than doing it all quite as algebraically as this anyway. But this is the most general kind of situation. And the benefit of doing this is that it allows us to think beyond just finding something about v squared. So we've got these two cases, these two situations to look at here with our fixed our object in a fixed vertical circle, like I was talking about. We can either have this kind of pendulum oscillating type of situation, or we can have the situation, if we give it more speed at the bottom now, we can have a situation where it goes around in a complete circle. And the perhaps natural question to ask is there any way of telling what it's going to do? Well, yes, there is, of course. And so we need to just think a moment, what do we need to have true? What needs to be true if the object is going to go round a complete circle? Well, if it's travelling up here, it's slowing down all the time as it goes up. It can't leave this circle, don't forget, so it's got to stay on this circular path. And essentially, as long as it doesn't stop before it gets to the top, then it's going to go all the way down. Well, okay, well that gives us some kind of condition, doesn't it? It means that we need to have v being greater than or equal to 0 when the particle is right at the top of the circle, and how else can we think about the top of the circle? Well, we can think about that just as being when theta is equal to 180 degrees, when the rod has turned through 180 degrees, it'll be at the top of the circle. So theta equals 180. If we still have v being greater than 0, when theta is equal to 180, then the object will complete a circle, will perform a complete circle. So here's how we might think about doing that. So this is for a complete circle. So for a complete circle, we want, and we don't need to worry about it being v being greater than or equal to 0. We can have v, as long as v squared is greater than 0. If it's equal to 0, then that means, well, it's just not going to happen practically, is it really? But what's going to happen there is the thing's going to stop right at the top. It'll be an unstable equilibrium. So actually we want v to be greater than 0, or v squared to be greater than 0. V can't be negative in this kind of situation anyway, because we're treating it as a speed. So as long as v squared is greater than 0 when theta equals 180, then we know that the thing is going to perform a complete circle. So we can apply our equation that we've just established there in these kind of situations. We want theta equals 180 in our v squared expression. So theta equals 180 gives us v squared equals u squared minus 2gr 1 minus, and now we've got cos of 180, but of course cos of 180 is minus 1, so we've got that going on there, and this means that v squared must be equal to u squared minus 4gr, and for v squared to be greater than 0, that implies that u squared must be greater than 4gr, or if you want it as something for u, we need to have u greater than 2 root gr. Although it's generally speaking left as u squared being greater than 4gr, because we're never really using u in any kind of situation, so best to keep it as u squared greater than 4gr. Also, there's a slight complication about squaring inequalities, which I don't want to get into here, or square rooting inequalities, which I don't want to get into here. That would be too much of a distraction. So as long as we've got sufficient u at the bottom of the circle, and sufficient being such that u squared is greater than 4gr, then the object is going to perform complete circles. Notice that that's regardless of mass or anything like that, totally independent of mass. And therefore, if we've got something where we've got u less than that, smaller than something which will give us 4gr when we square it, then the alternative situation will be where we're not completing circles and we've got that oscillating pendulum type of motion. So that's fixed vertical circles. We can then of course go on to think about what angle the particle will reach to in the case where it doesn't stop, and that would just be a case of setting v equal to 0 and solving your equation for theta instead this time, rather than substituting a value for theta into it. And we can go on and think about tensions. Once we've got an expression for v squared, then we can use our tension and a component of the weight being equal to mv squared over r, and we can start working on forces and all of those sorts of things as well. So the other case to look at is when things can leave their circular path, and that will come up in a different video.